So first thing I would do for this problem on our 5-minute check is I highlighted some, if you might notice, the decreasing sections of the graph I've made red, increasing sections of the graph I've made green, and the constant flat section, the horizontal section, I have made blue. Okay. Now, if we're going to sketch the derivative, the first thing I look for, do I have any maxes and mins? I know that our function in that particular spot is equal to 0. Okay. Now I'm going to look for any linear sections. A linear function, the slope of the tangent is equal to the slope at that particular location. So let's do that. So this particular location, the slope of a horizontal line is 0. And if we check out this line, it is going up 1 over 1, up 1 over 1 forever. So its slope is 1. So all we've got to do is create a line from that section that mirrors that slope or parallel to that line. So the only ones we really have to contemplate are these two sections. Okay. Now we're going to have to guesstimate here. So, just guess best you could. So let's see, it goes through this point real nice. So let's kind of draw a rough sketch of a tangent line. And it looks kind of like it's a slope of 2 there. Wouldn't you say it looks kind of like it's a slope of 2? So when x is equal to 1, the slope looks like it's about 2. And then what's weird about this function, let's look right here at that point. The derivative is undefined technically at that point because at one side it's here and then at one side. So we're going to change this right here to an open circle. Let's change this right here. Actually, I have to change a few different things. I'm so not, no. Okay, anyway, let's change this to an open circle. Okay. I said that the slope or the slope of the line mimics the slope of the tangent. The derivative is the slope of the tangent. So the slope of this line is 1. So then it jumps to a height of 1 forever. I'm so sorry. Totally different. Anyway, so I'm going to guesstimate what it is right here. Would you say it's it's higher than 2, I think. Let's just go for the sake of it that it's 3. It would have to be an open circle there. So our graph looks like something, I don't know, something like that. Now let's go this side, okay? So this right here looks like it's -2. So, and at x value of -6, I seem to be at -2. This seems even steeper way up here. Let's go that's -3 or 4 or something. So you'll notice it's going to keep going. So let's kind of analyze what's happened. Actually, this piece almost looks linear, truthfully. But anyway, let's look at what's happened. A line became a constant. If two lines are connected but with different slopes, they won't connect right because one will jump to its slope. If one is a slope of 2 and one is a slope of 7, one will be up at 2 and one will be up at 7. So those parts disconnected. This curvature here, if it's a quadratic, if we're assuming that's part of a parabola or something, I believe this might actually end up being kind of linear when it's all said and done. But anyway, as long as you can kind of guesstimate and follow what we just did there, and you're good to go. Okay. Now we are going to jump to 2-3. Now 2-3 is great because for the very first time, we are going to look more at the shortcuts, the differentiation formulas. So you know that long difference quotient stuff we've been doing, f of x plus h minus f of x all over h, and then having to reduce it down and stuff. We can just jump right to the formula. Now, if I ask you to use the definition of the derivative or the difference quotient, then you'll show me everything, but you'll know what the answer is ahead of time, almost, or pretty darn close. Here's the things you need to know. Remember how I said that if it got a horizontal line, the slope is always 0, and that's what that little section was at 0. So that's a rule that you can learn. If our function is a number, a constant, the derivative is always equal to 0. So the derivative of a constant function, because the slope of that line is 0, the constant function's derivative is always 0. So if I say I have a function, f of x equals 7, what is the derivative? 0. F of x equals 20, what's the derivative? 0. The derivative of a constant, a number, is always equal to 0. So if I say f of x is 2, and I want to know what's the derivative, it's always equal to 0. It is just what it is, okay? So the derivative of a constant is a number. You got to know that. It's the derivative of a number is always 0, okay? Now let's talk about power functions. If we start out with a power function, f of x equals x to the n, if our power is x to the first, since that is a line with slope 1, our derivative is 1. If it is x squared, the answer is 2x. If it is x cubed, the answer is 3x squared. If it is x to the fourth, the answer is 4x cubed. Do you see a pattern? Anybody see what the pattern is? Okay, let's go up to the top. The derivative of x to the first is 1. The derivative of x squared is 2x. The derivative of x cubed is 3x squared. The derivative of x to the fourth is 4x cubed. Anybody notice the pattern? Anybody notice what's happening? Look at the pattern. The number in front is the power. The power is 1 less. So here's our rule. I think we're going to write it on the other page as well. If we start out with a power function, we're going to do exactly what Jeremy said. We're going to drop that power down in front. The power is going down by 1. You're going to drop that original power down in front. The power goes down by 1. Look what happened every single time. That's an x to the first. We drop down a 1 times an x to the 0. X squared, we drop down the 2, the power becomes an x to the first. Drop down the 3, power goes down by 1, x squared. Drop down the 4, power goes down by 1, x cubed. It is a pattern. You have to know it. It's not going anywhere. It's going to be used for the rest of the year. That is super important. Okay. So that's the rule that we see right here. The derivative of an x to the n drops down in front. The power goes down by 1. The derivative of a power function. The power drops down in front. The power goes down by 1. If you have a constant times a function, don't worry about it. It just comes along for the ride and multiplies by whatever that particular derivative is. So, an example, let's say we have 2x to the fourth. We just learned what x to the fourth did, right? So the derivative of that is 2 times whatever the derivative of x to the fourth is. We already said what it was. The power drops down in front. The power goes down by 1. So the derivative of that is 8x cubed. Did we have to do that long f of x plus h minus f of x over h? No, because we know the rules now. Okay, so if there's a constant there, it just comes along for the ride and multiplies by whatever the original one was. So an x to the fourth we know is 4x cubed. So it's just 2 times 4x cubed. Okay. If two functions are differentiable, we can take the derivative of each individual piece. Let me show you an example of that. Say we have some function. Let's just go with some things we know already. X to the fourth plus x cubed. I know what the derivative of x to the fourth is. I know what the derivative of x cubed is. So the derivative of that addition, don't worry about it. Do the derivative of each individual piece. So that's going to be 4x cubed plus 3x squared. Look what happened. For our x to the fourth piece, power dropped down in front, power went down by 1, 4x cubed. For the x cubed piece, the 3 dropped down in front, the power went down by 1, x squared. Now, the reason this works is because of our limit laws. The limit law said that if the limit of two functions were added, just add the individual limits. Remember, the definition of derivative has a limit in it. So if we have two individual functions, you can evaluate each one separately. And that's great because even if we have some function that's a long polynomial, who cares? Do each individual piece one at a time. So x squared becomes 2x, 2x becomes 2, 3 becomes nothing. The derivative is 2x plus 2. They're amazing, lovely formulas. You just got to memorize the formulas. Okay. So it doesn't matter if you add them or if you subtract them. Just individually do each derivative and subtract them. Example. Say we have 4x cubed minus 3x. That's an easy derivative to do. The first piece, the power drops down in front, multiplies by whatever was there. The constant just stays. 4 is just hanging around for the ride. And then here, that's negative 3 times 1, which is negative 3. There's your derivative. Did you have to do any formula or that big old weird stuff? Think about what we had to do if it was a cubed. No, we got to learn the one before we learn the other. Otherwise, it's kind of cheating a little bit. This is theoretical calculus, so you need to know the theory behind it. I never said it was good, but so you have to know these formulas. These are going to be your lifesaver. Just perfect, wonderful formulas. Okay, so make sure we're going to learn all, we're going to, kind of make flashcards or put on our vocabulary all those different formulas so we have it. So let's look how easy these are. Let's look at A and C. If we want the derivative of x to the 6th, just drop your 6 down in front, power goes down by 1. The answer is 6x to the 5th. T to the 4th, 4t cubed. See how easy that is? Now, it doesn't even matter if we have powers that are disgusting like 1,000. Drop the 1,000 down in front, power goes down by 1. We could not do that with the formula. We just couldn't. And then here, don't worry about that notation. That's just saying take the derivative of r's. So it's 3r squared. Power drops down in front, power goes down by 1. Think about how wonderful those formulas are. Nice, perfect, wonderful. I told you this lesson was so nice. But you just have to know your formulas, okay? Any questions about example 1? Now, there are times where you're going to look at it and go, what in the world do I do? Usually there's a rewrite that's going to allow us to use a formula that looks nicer than what we started with. Now, eventually we're going to learn a rule that if we have a fraction, there is a rule we can do. But if we can rewrite it as a power function, we never have to do that because we have a rule for power functions. So rewrite this function first using our rules of powers. That's just x to the negative 2. Once it's a power function, then we can just use our power function rules, and then we got it. So the derivative of that, the power drops down in front. The power goes down by 1. So be careful with that. We're subtracting 1, and since the original power was negative, it just becomes more negative. Now, many times we will rewrite this without a negative exponent. That's pretty common. Or if it's a multiple choice test, that's not going to show up. So you do need to know that that's the same as that. Am I okay with you stopping here? Because I hope that you know that those two things are equivalent. Yes, but you have to know that these two things are equivalent. But I mean, feel free to stop here, but these two things, if it's a multiple choice test, which some of our tests might be, this is what it's going to show up as. So make sure you understand how those two things are related. The only piece that flips down to the bottom is the piece with the negative exponent. That's why the negative 2 stayed in top. It's a positive power. Only one that's negative is the x. Everybody good with example 2a? Okay. Now, again, you have to remember your rules of exponents. Remember, that is the same as the power of n over m. The power on the inside is your numerator. The index is your denominator. The power on the inside is your numerator. The index is your denominator. Just watch that. So rewrite this first as x to the 2/3, and then it becomes a power function. Otherwise, there's no way to do this problem. You have to do that. So the derivative, you drop the 2/3 down in front. The power goes down by 1. 2/3 minus 1 is the same as 2/3 minus 3/3, or negative 1/3. So the derivative is x to the negative 1/3 power. Now, how do you write that? How would that show up on a like a multiple choice test? So you might see that as this. That 1/3 is a cube root, but they're not going to, they might rationalize it. So that would pop the cube root to the bottom. Since we only had 1 and we need a cube, we would actually need to multiply top and bottom by the cube root of x squared. We need 3 of them to make it work. So the one in the bottom would be an x, but the one in the top would be the 2 extra I needed to make it a full one. Now, I'm not going to, I am totally good with you stopping here. But again, you need to know which is the correct way to write it. I don't rationalize cube roots very often, so that's usually an okay way to write it. Okay. So sometimes it's going to require us to remember our rules of powers, remember our rules from algebra that allows us to do a rewrite, which will make it then a differentiable quantity. Everyone good with example 2a and b? So then that leads us to find an equation of tangent lines. Okay, so let's look. The first thing we want to do, anytime we are finding the equation of a tangent line, the first thing we do is we find the derivative. The second thing we do is we find the slope of our tangent by plugging in our information. The third thing we do is always y minus y1 equals m times x minus x1. So that's really the strategy every single time. Now we have some really good techniques to find step 1 that we didn't have before, right? So that's why we're revisiting this without some of the complications of the gross formula. So the first thing, let's rewrite this as a power function, that's technically x to the 3/2. Why? Well, that's x to the first times x to the 1/2. If the bases are like and we're multiplying, add the exponents. 1 and 1/2 is 3/2. Rewrite it as a power function because now we know an excellent rule about power functions. The derivative, you drop the power down in front, the power goes down by 1. Yay. Okay. So now we have that derivative. That's our first step. So our slope of our tangent, we just have to plug, using the 0.11, we have to plug in an x value of 1. So that'd be 3/2 times 1 to the 1/2. Well, luckily for us, 1 to any power is 1, and so that's 3/2. So step 1, we found the derivative. Step 2, we plugged in the x value to find the slope of the tangent. And then our last step is to use y minus y1 equals m times the quantity of x minus x1. Now, what are we using? Well, our point is 1, 1. Our slope is 3/2. So you're just using the point provided. If they only gave you the x provided and not the y value, you might have to plug it in to find the point. But we're just plugging the stuff in. Okay, so let's do it. So it's y minus 1 equals 3/2 times x minus 1. I'm good you stopping there. I don't need you to go further than that, okay? I don't really need you to go further than that. And then if you look at my picture for a moment, at the point 1, 1, our slope went up 3 over 2. Wait, I'm sorry. Up 3, 1, 2, 3, over 2, 1, 2. We have a slope of 3/2. We went through the point 1, 1. Okay? So it should make sense that, and that's a great way, guys, to check your work. Go into Desmos, type in y equals x times the square root of x. Do the original version because in case you did a mistake with the actual conversion, you'll find it. Then type in your equation of the tangent line, exactly what you see here, that y minus 1 equals 3/2 times x minus 1. If they don't skim each other right at the point 1, 1, you did it wrong. The Desmos, the algebra, and the graphical interpretation should always go together, or one of them is wrong. Okay, everybody good with example 3? Some more derivatives to do, rather, just we're trying to, get in the habit of doing them quickly. So this is just the derivative of 3x to the 4th would be 3 times whatever x to the 4th is. So that's 4x cubed. So that's 12x cubed. So remember, look what happened. The 4 dropped down in front. The power went down by 1. The 3 just hung along for the ride and multiplied by whatever our final answer was. So that's why that's that. The derivative of negative x is negative 1 times 1x to the 0. Now, I wrote all those. I want you to just get in the habit of saying the derivative of a linear function is its slope. So the answer is negative 1. Why? Well, that's just 1. X to the 0 is 1. So that's negative 1 times 1 times 1. It's just the slope. It's just negative 1. So you don't have to show all that, but that's why it happens, that linear function is just the slope. Everybody good with that? Okay. And then there's example 5, it's just a big polynomial. You're just going to go down the list, taking each individual term. So this first term would be 8x to the 7. Then keep the 12 there and multiply by the derivative of x to the 5th, which is 5x to the 4th. Same thing here, negative 4 times the derivative of x to the 4th is 4x cubed. 10 times 3x squared minus 6 plus 0. Do you have to write the plus 0? No, I'm just kind of reminding you how those rules work. Let's make it pretty. Let's make the final answer 8x to the 7 plus 60x to the 4th minus 16x cubed plus 30x squared minus 6. Think about if you had to do the difference quotient to that big long polynomial. No. Okay. For a long time, they, before Newton and Leibniz, they knew this pattern was happening. They were doing the long formula, but it took minds like Newton and Leibniz to go, there's a quicker method. And so that's kind of, the great thing about these formulas. Okay. Okay, now let's take a look at this problem. It says find the points in the curve, and x to the fourth minus 6x squared plus 4, where the tangent line is horizontal. Any line is horizontal when the slope is equal to 0. So if the tangent line is horizontal, the slope of the tangent has to equal 0. What is the slope of the tangent? Well, that's the derivative. So this problem is really saying, where is your derivative equal to 0? So let's find what the derivative is. The derivative is 4x cubed minus 12x plus 0, and that has to equal 0. So you have to get into the habit, when they mention anything to do with tangent lines, the derivative gives us the slope of that particular line. And a horizontal line, it has a slope of 0. So you're blending that two pieces of knowledge in your head. Now, to solve that, just factor it. Factor out a 4x to start, because both terms are divisible by 4x, leaving us with x squared minus 3. And so I'm going to show this a few different ways. You can write that as x plus the square root of 3 and x minus the square root of 3. Or you could just kind of do x squared minus 3 equals 0 individually. But you guys tend to forget the plus or minus in front. So by using the difference of squares, writing it in two pieces helps students remember that there are two pieces. Do you have to? No, not if you remember that when you inflict the square root, put that plus or minus on there. However you do it, we get answers of 0, negative square root of 3, and positive square root of 3. So that means that when when we have an x value of 0, when we have an x value of negative square root of 3, when we have an x value of positive square root of 3, we will have a slope that is horizontal. So that's the maxes and mins. Yes. I was just getting to that. Yep. So what was mentioned here is the points. So we're not done. You do have to find the matching y value. Okay. So if we plug in 0 up here, we get 4. So that is the 0.04. That's an easy one. The other ones, when we take negative square root of 3 to the fourth, when you first square it, you get 3, and then square it again, get 9. And then minus 18 plus 4, that is negative 5. So that's the point negative radical 3, negative 5. And if we plug in positive square root of 3, we also get negative 5 because of the symmetry and stuff. This is an even function. It does have y-axis symmetry, so it makes sense if something happens at negative square root of 3, it also happens at positive square root of 3. But again, Desmos is your friend. If you looked at Desmos, the tangent line is horizontal at the peaks and valleys, at our mins and maxes, our relative mins and maxes. So this one has 3 relative mins or maxes. So it should have 3 horizontal tangent lines. You can even start to classify them, and we're going to eventually talk about the classifications. These are absolute minimums of the function, and this is a relative maximum. And we'll classify them more at a later date, but the slopes of the tangents being equal to 0 is a helpful thing. It pinpoints some locations more easily than other techniques. Everybody good with example 6? Now, there's times where we're going to have a function where it is a multiplication of 2 things that is not easy to differentiate. Now, I'm going to have to show you because of what our limited knowledge is right at the moment. I'm going to have to show you with something we can multiply out, but I'll prove it to you after we're done. But this saying, I'm going to say again and again and again and again. So you're going to say it right now with me, okay? Just do it. And because we got to get into our brain, we're going to say it twice, okay? So everybody just say it with me. Just deal with it because it's going to help our brains. So the product rule tells us that if we have 2 functions that are differentiable, then there's the rule. Ready? The first times the derivative of the second, say it with me. The first times the derivative of the second plus the second times the derivative of the first is our derivative. Okay, let's do it again. Ready? So if we want to take the derivative of f times g, it's going to be the first times the derivative of the second plus the second times the derivative of the first. Okay, so that rule is super important. We're going to have a product rule. We're going to have a quotient rule. We have to have them memorized. So I'm going to say the first times the derivative of the second plus the second times the derivative of the first a lot. But you're going to get into your head that way a little better, okay? So please make sure you understand what the product rule is and what it allows us to do. If we have a function f and g and we need to take the derivative of it, we can just take the first, write it down, times the derivative of the second, using some of our rules, plus the second, write it down, times the derivative of the first. So we're always going to use that technique to help us. So the product rule is something we have to memorize. There's just no 2 ways about it. You just got to memorize it. So I'm going to show you a very silly example that we don't technically have to use the product rule, but this will help show you that it does work, that I didn't just make this up. Okay, so we have 2 functions multiplied together. See, those 2 things are multiplied together. To take the derivative, if we were to use the product rule, which we don't have to, but we could, it would be the first, write it down. So I'm going to call this f and g. So it's the first, write it down, times the derivative of the second. So that's 7 times 4, or 28 x cubed, plus the second, I'm going to write it down, times the derivative of the first. I'm going to do that multiplication. Everybody see how I got that derivatives? Okay, so this is the first times the derivative of the second plus the second times the derivative of the first. Okay, and so then 6 times 28 is 168 x to the 6th. 7 times 18 is 126 x to the 6th. We can add those up. 126 plus 168 is 294 x to the 6th. Okay. Now let's do it as a little check without the product rule. So if I were given this problem, if I was a calculus student and I was given this problem, I would never do the product rule. It's done. You don't have to use the product rule. But this is just a good example that the product rule works. When are we going to use the product rule? Let's say we had x squared sine of x. Can we technically multiply or combine x squared and a sine of x? No, that's when we use it. So eventually you'll know all of the shortcuts to find the derivatives of the trig functions, exponential functions, all kinds of different functions. We'll know the shortcuts, okay? Let me show you if I didn't use the shortcut. Look how easy it's going to be. If I mush those, so it wasn't a product anymore, it was just a thing. 6 times 7 is 42. That would be x to the 7th. We know the derivative of that, don't we? We drop the 7 down in front. The power goes down by 1. Guess what 42 times 7 is? 294. So there are times where if you can mush the things together, you don't want to use the product rule. It's more complicated than just using one of our individual power rules or something like that. So like if we had x plus 2 times x plus 3, you have two choices. You can multiply them and then do the individual terms, or you can do the derivative of the first times the second plus the second times the derivative of the first, and so on. You can do the product rule. There's a quotient rule. There's a quotient rule. Okay, guess what? We're going to say it together here in a second. But let's look. If I have two functions, f and g, and I'm dividing them, so f divided by g, here is the quotient rule. So ready? Let's say it. We're going to say it 2 times. Ready? The quotient rule says the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. You're going to have to memorize it. Let's say it one more time. The bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Even if you just remember that the bottom starts first and it's over the bottom squared. The bottom, here's why. The quotient rule has a minus between them right here. So the order matters. The product rule doesn't. It has a plus between them. So if you mess up the order, it's going to be okay. You mess up this order, it's not going to be okay. You'll get the opposite of what you want. So you always start with the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. That's just is what it is, okay? So let's look at this particular function. Now, if there was a way that I could factor the top, factor the bottom, cross things out so I didn't have a quotient, I would do that. This is a perfect example that I can't. So I have to use the quotient rule, okay? Okay, so let's go about doing it. So it is the bottom. Write it down, use parentheses. The bottom, we're going to write down the bottom. That's always your first step. Bottom times the derivative of the top. Just use your rules of how do I take the derivative of that? 2x or x squared becomes 2x. X becomes 1. Negative 2 becomes 0. Minus the top in parentheses times the derivative of the bottom in parentheses all over the bottom squared in parentheses. Okay, so let me say it again. The bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. I will tell you the places that my students in the past have screwed this up. They don't start with the bottom, so they'll switch their tops and bottoms, or that top two pieces, they'll switch them. That's common. They won't use parentheses, so their distribution gets all mucked up. Okay, so please use parentheses. Bottom times derivative of the top minus top times derivative of the bottom over the bottom squared. Okay, now for us to actually do this, let's actually FOIL out everything we can. So I'm going to multiply these two. So I'm going to get 6x to the 4th plus, no, I made up 6. It's 2x to the 4th plus x cubed plus 12x plus 12. Now, since this is only one term and this negative, I'm going to distribute negative 3x squared to everything. Did I mess something up? It is 12x plus 6. So I'm going to distribute on the end negative 3x squared to every piece. So we're going to get negative 3x to the fourth, negative 3x to the third, plus 6x squared. I am never, let me say it again, going to multiply out the bottom. I am never going to multiply out the bottom. Remember when we were doing stuff with the rules and I would say, okay, I won't say never, 90% of the time, just leave the bottom. Always leave it to begin with anyway, okay? On the top, there is probably going to be some stuff that cancels or combines. So we've got 2x to the fourth. We'll start with the highest and go to the lowest. Minus 3x to the fourth. That's minus x to the fourth. And then we've got an x cubed and a minus 3x cubed. So that is a minus 2x cubed. And then we have a 6x squared. And then we have a plus 12x and a plus 6. Now, there may come a time where we would need to possibly factor this thing. This is not one of those times. So just leave it because it is what it is, okay? But think about if we had to put that into the formula, how yucky it is. But because we know this rule, that it's the bottom times the derivative of the top minus top times derivative of the bottom over the bottom squared, we don't have to do that. So we can just follow that rule, okay? So that is an example of why we have to use the quotient rule. I can't really show you a good example of the product rule yet until we learn the trig functions, and then we'll throw that in there. How much time do we technically have? Okay, we got it. Okay, last example. It says find the equation of the tangent line and normal line to the curve at the point 1, 1/2. So we're going to focus on the tangent line because if you know the tangent line, the normal line is kind of a bonus for free. You kind of get it as a good example. Okay, so remember the rules we talked about before. You always find the derivative, which gives us the slope of the tangent, which gives us y minus y1 equals m times x minus x1. Okay, so we're going to follow those 3 steps to find the slope of the equation of the tangent line. Okay, so I'm going to rewrite my function as an x to the 1/2 over 1 plus x squared. This one, I have to use the quotient rule. There's no other rule that I can use to find the derivative of this. Okay, so in parentheses, I'm going to write down the bottom times the derivative of the top. Drop the power down in front, power goes down by 1. Minus the top times the derivative of the bottom, all over the bottom square. So that's step 1. Now, step 2, what's great is I am not in any way, shape, or form messing with that junk that I found in step 1 because I have numbers to plug in. So why simplify something and then simplify it incorrectly just to plug a number in? We can simplify numbers a little easier. So the x value we want to plug in is an x value of 1. So let's plug an x value of 1 into that. 1 plus 1 squared is 2. 1 to any power is 1, so that's just going to be 1/2 times 1. 1 to any power is 1. 2 times 1 is 2. 1 plus 1 squared is 2, and then squared. Now, look how much easier it is, unless we wanted to try to simplify up above. Don't torture yourself. Okay, so that's going to be 1 minus 2 over 4. We found the slope is negative 1/4. Yeah, that's not so bad. Okay, so the equation of our tangent line is y minus y1 equals m times x minus x1. Or, yeah, okay. We're done. Now, they did say a normal line. A normal line is the reciprocal, the slope of a normal is the reciprocal of the slope of the tangent. So just flip it over. So the slope of our normal line, the flip of negative 1/4, because they're perpendicular. Oh, it's the opposite flip. You got to change the sign and flip it. It's perpendicular. Is instead of, if you flip negative 1/4, you get -4, it would be +4. So you just do it again. So it's y minus y1 equals the new m. I didn't put the new m, I didn't put this right. I'm so sorry. Anyway, so the new slope is 4 times x minus 1. You'll notice the only thing that changed, these two lines are perpendicular. Okay, the normal line and the tangent line are perpendicular. So if you were to put this gross equation, y equals the square root of x all over 1 plus x squared, put it into Desmos. Put in your first equation we found. It should be a tangent to it. It should skim it. This one, the new normal line, it will be through the same point, but it'll be perpendicular to the tangent. So the normal and the tangent should be the, yes. I'll have to look that up. There's probably some history of why it's called that. And then you got some homework.